Hello, welcome to this lesson on the students' T distribution. This lesson includes a brief introduction to the T distribution and then some theorems and facts related to the T distribution. Uh, they include uh, T quantiles, connection with the sample mean and sample variance, the two sample T distribution, the T distribution with Sarath weight degrees of freedom, a T distributed ratio involving a quadratic form, non-central T distribution, and R functions for the T distribution. So let's start with the introduction. The student's T distribution, usually called the T distribution, was introduced by William Gosset, who published under the pseudonym Student. Why did he publish his paper under the pseudonym Student? Well, he was working as a statistician for the Guinness Brewery in Dublin. Guinness generally prohibited employees from publishing research that might reveal commercially valuable information. So therefore, when Gosset published his paper in 1908 with the title The Probable Error of a Mean, he used the pen name Student. So that's why today it's called Student's T distribution. The T distribution belongs to a family of distributions. And this family is parameterized by the degrees of freedom, usually denoted by the Greek letter nu. This nu is a positive number. Generally, in practice, it is an integer, but theoretically, it doesn't have to be an integer. It can be a positive real number. Different values of nu produce different members of the T distribution family. Now, if a random variable capital X has a T distribution with, say, nu degrees of freedom, then we write it as X has a T nu distribution, where the degrees of freedom is written in the subscript. Now, this T distribution is very, very useful. The T distribution is used extensively in statistical inference, mainly about population means when the population variance is unknown. Now let us see how this T distribution arises in general. Suppose you have a standard normal random variable Z and a chi-square random variable U, and suppose Z and U are independent, right? Suppose Z has a normal distribution with mean 0 and variance 1. So that's a standard normal distribution. And U has a chi-square distribution with, say, new degrees of freedom. And if Z and U are independent, then this ratio, let's call it T, capital T, Z divided by square root of U divided by its degrees of freedom. That quantity has some distribution, and that distribution is called the T distribution with new degrees of freedom. That is the most common way of writing the T distribution as a ratio of a standard normal and a chi-square random variable where those two are independent. What are the properties of this distribution? So these are the main or principal properties of the distribution. The density function of the any chi-square distribution, sorry, not a chi-square, the density function of any t distribution is symmetric around 0, right? The density function of any t. Here, when I say any t, I'm talking about something called the central t. Later on, we will talk about something called non-central t. Here, I'm dealing with the central t distribution. So the density of any central t distribution is symmetric around 0, and it also has a bell shape, like a normal distribution. Right? But the distribution has heavier tails than the standard norm. Right? Standard normal distribution is also symmetric around 0. It also has a bell shape. But we know that for a standard normal distribution, the density becomes almost 0 when Z becomes negative 3 or positive 3. Right? When Z is less than negative 3 or more than positive 3, then the density function of a standard normal is almost 0. But for a t distribution with some new degrees of freedom, it's not like that always. Generally, it has longer tails, or we say heavier tails, than the standard norm. Uh, Now, what are the mean and variance of a random variable with a t new distribution? If x has a t new distribution and if nu is greater than 1, expected value of x is equal to 0. As I mentioned, it is symmetric around 0 as well. If nu is greater than 2, then the variance is equal to nu divided by nu minus 2. Right. Uh, so we can see that when nu increases, nu and nu minus 2 becomes very, very close, and therefore when nu is increasing, variance of x will be converging to 1. But a t distribution with degrees of freedom uh, equal to 1 doesn't have a mean. That means its mean is undefined or infinity, right? Because it has very, very, very long tails, thick tails, without coming to 0 as quickly as in the standard normal, right? So therefore, when you integrate x times the density function to get the expected value, uh, it becomes infinity. But if nu is between 1 and 2, greater than 1 and less than or equal to 2, mean exists. But in that case, the variance is infinite. Right? So the variance is finite only if nu is greater than 2. If nu is between 0 and 1, not only when nu is equal to 1, between 0 and 1, mean and the variance both do not exist. Uh, as I mentioned, generally the t distribution has heavier tails than the standard normal, but as the degrees of freedom increases, the corresponding t distribution converges in distribution to a standard normal distribution. Right? So T nu converges in distribution to a standard normal distribution as the degrees of freedom increases. So now we will look at this property just to see actually that T nu converge into the standard normal in distribution. I have a Shiny app, so let me use that to show you that the distribution of a T new distribution converges to a standard normal as the degrees of freedom is increased. So here I have a central T distribution that is shown with this red color graph, uh, and then area under the t distribution. In this case, I am showing you the standard normal distribution with this dotted curve, not the dotted dashed curve. Uh, the red curve is the t distribution. In this case, I have the t distribution with 1 degrees of freedom. Uh, you can see that the normal density function becomes almost zero when z becomes -3 or less than that, and when z becomes +3 or more than that. Right? But for the T1 distribution, the density is not uh, at least close to zero at this point, right? Uh, so actually it goes a long way to the left and long way to the right without coming to close to zero, right? This particular T distribution with 1 degrees of freedom has another name. It is called the Cauchy distribution. Cauchy distribution. And usually in undergraduate basic levels, we learn that Cauchy distribution as an example of a distribution whose mean and variance does not exist. But it is symmetric. The distribution is symmetric around zero. And it has a bell shape also, right? The bell, of course, the curvature of the bell is different than in a standard normal or any other normal. Right. So let's see what happens if we increase the degrees of freedom. Right. So now when I increase this thing, you'll see that how the density function of the T new distribution is coming close and close to the shape of the standard normal distribution. Right. So here I have, okay, let's consider, say, for example, 20. Right. So I have here the T distribution with 20 degrees of freedom and the standard normal. So superficially, if you look at it, one might say they are almost the same. But of course, in the tails, there is a big difference. For example, if I look at the 0.975 quantiles of the two distributions, for the T distribution is 2.08, that almost like 2.1. But for the standard normal, it is 1.96. So that difference may be important in statistical inference, especially when you are making some decisions based on hypothesis test, and also when you are constructing confidence intervals, uh, that may not be accurate enough, right? But if you increase the degrees of freedom further, right? So for example, 30, when the degrees of freedom is 30, I have now T30 distribution and standard normal. Now, well, the T quantile, 0.975 quantile of the T distribution is 2, and Z quantile is 1.96. And at this point, usually people take 1.96 to be close enough to 2, and therefore, when the degrees of freedom is 30 or more, usually people take the corresponding T distribution um, as an approximately a standard normal distribution, right? And if degrees of freedom is increased further, like when it up in sport go up to 100, say for example, so in that case, they are almost the same on top of each other. You can see that you cannot even see a difference, and the quantiles, the tail values are also very very similar, right? The usually the difference exists in the when for a reasonably large degrees of freedom, the difference mainly exists in the tails, right? Because uh, the T distribution with a small degrees of freedom usually has very very heavy tails or long tails, right? So it takes some time when you are increasing degrees of freedom. It takes some time for the tails to be short and come to come to close to zero, as in the standard normal around -3 or +3, nu has to be large, right? Okay, so that is a demonstration of the convergence of the T nu distribution to the standard normal as the degrees of freedom increases. Now let us look at another important thing for a T distribution. Those are the T quantiles, right? These T quantiles are very useful again in test of hypothesis because they are involving decision rules as well as they are important in constructing confidence intervals, right? The important thing about these quantiles is actually their notation, right? Different authors seem to use slightly different notations for these quantiles, right? So therefore, we now look at about three types of different ways of notations for these quantiles. For example, for the same value as a quantile, they may be denoted by different authors using different notations. So the first one, suppose that X has a T nu distribution, and then for a given probability P, where P is between 0 and 1, the value K satisfying this probability statement is called the pth quantile of the T distribution with nu degrees of freedom, right? So if we can find out, when we find out the value K satisfying this probability statement, that K is called the pth quantile of the T distribution with nu degrees of freedom. And some authors denote that K by T P nu, where P and nu are appearing in the subscript T, and then first value in the subscript is this P, the probability associated with that. The second value is the degrees of freedom of the chi-square distribution. So that is one notation for the pth quantile of a T nu distribution. Now, mathematically, I mean, you can find out for a given P and given nu value, we can find out this value. For example, using R. R has the command Qt for this, right? So the quantile with probability P and say the degrees of freedom is equal to nu can be obtained using the function Qt, and it is applied like this: Qt within bracket. The first argument is the probability P. The second argument is the value nu, right? So for example, if I use a P equal to 0.95 and nu equal to 10, I get, using this command, I get 1.812, approximate to 3 decimal places. So that means the probability, if X has a T distribution with 10 degrees of freedom, then the probability that X less than or equal to 1.812 is equal to 0.95. So therefore, this value is 1.812 is denoted by T 0.95 comma 10. That is one way to denote it according to this convention. So the probability that capital T, in this case, not T actually, I have used X here. So the probability X less than or equal to this value is equal to 0.95, right? So sometimes people use T to denote the random variable with the T distribution. And I also was using that, and I forgot to change that when I draw the graph, right? So that's why T is appearing here. But according to this notation here, this should be X here. The probability X less than or equal to this quantity will be equal to 0.95. Okay, so that is one way of denoting the pth quantile. The same value will be denoted by some other authors in a different way. Uh, for example, in some books, that the same value will be denoted with some T alpha nu notation, where it's the same actually, only that usually in this case, in order to denote the probability, they use alpha because it is related to something called the level of significance in a test of hypothesis, and it is related to the level of confidence in a confidence interval, right? So in that case, generally it is denoted as alpha. But here, this T alpha is denoting something called the upper tail critical value of the T distribution with new degrees of freedom, right? So generally, when you write down as T alpha nu, it may mean the upper tail critical value with upper probability alpha and T distribution with degrees of freedom nu. Right. So for a given probability alpha, where alpha is between 0 and 1, uh, this is the value k satisfying the probability that x greater than k is equal to alpha. Right. X greater than k is equal to alpha. Right. So in that case, this k is denoted as T alpha nu usually. Right. So therefore, the probability that x greater than T alpha nu will be equal to alpha, right? And even in some books, some authors use the notation with the reverse order of these two numbers. In that case, some people write down as T nu alpha instead of T alpha nu, right? So you might see when they're talking about these critical values, T alpha nu or T nu alpha, but most common one is T alpha nu. But anyway, in this case, there will be no confusion because one of these numbers is always greater than or equal to 1 in practice, right? Greater than or equal to 1. But the other value, alpha, is always between 0 and, right? So whenever you see these two numbers, you will be able to decide which one is the degrees of freedom and which one is the alpha, right? If I uh, look at the previous example, when the probability below some k is 0.95, of course, for the same value, the probability above that value is equal to 0.95, right? Sorry, 0.05, right? When the probability below some k is 0.95, probability above that value is 0.05, right? So therefore, according to this notation, the same value that we had earlier, 1.812, will be denoted as t.05, 10 instead of t.95, 10. Right? So that is where the confusion can occur. So therefore, we have to be careful when you are reading books and also when you are applying these things, you have to be careful. Right? Especially if you are including these notations in your thesis or in your research paper or in your answer scripts in the exams, it is always better to define your notation, whether you are using the previous notation uh, with indicating the probability x less than or equal to the quantile is equal to p, or whether you are uh, using that notation, your notation, to indicate the probability above the k, right? So in this case, this value still is the same value, but now it is denoted as t.0510 instead of according to this notation. It might even also be denoted as t 10, 0.05, right, according to this notation here. But in that case, as I mentioned, definitely we know 10 is the degrees of freedom and 0.0p is the alpha value. So there will be no confusion in that case, right? So since the notation for T distribution quantiles and critical values varies among books, or is varied by according to the author, the convention being used should always be critically or carefully checked. Right. Okay. Now we will look at the connection with this T distribution with the sample mean and sample variance. This is what is important for the statistical inference, right? So suppose you have a random sample x1 up to xn from a normal distribution with mean mu and variance sigma square. In other words, x1 up to xn are IID normal mu sigma square random variables. IID means independent and identically distributed. And using these x1 up to xn, let us define, as we know, x bar will be the sample mean, and S square is this quantity with the divisor n minus 1. Then, because x bar has a normal distribution, in this case, we mean with mean mu and variance sigma square over n, we know that this quantity x bar minus mu over sigma over root n has a standard normal distribution. So that's a very preliminary result. And we also know something related to S square. That is n minus 1 times S square over sigma square has a chi-square n minus 1 distribution. Right. Both of these happens when the data are IID, right? Normal, IID normal. When the data are IID normal, in addition to these two, we also know that x bar and S square are two independent random variables, and therefore this z and u are also independent, right? So therefore, if we look at this ratio, z divided by square root u divided by the corresponding degree of freedom, right? If you substitute for the z and u from these expressions, previous expressions, we get this expression here. X bar minus mu over S over root n, and now root n goes to the numerator because of that. And according to the way that usual T distribution arises that I mentioned little earlier, this should have a T distribution with n minus 1 degrees of freedom. Right. So that's coming from this previous result here. This is how T distribution arises usually with the standard normal and chi-square, which are two independent random variables. Then this quantity has a T nu distribution, where nu is the degrees of freedom of this chi-square random variable. So using the same result, now we know that this quantity, because Z is standard normal, U has a chi-square distribution with n minus 1 degrees of freedom, and these two are independent. Therefore, this should have a T n minus 1 distribution. Now, this is the same thing I have written in a different way. I have divided by square root n. So let me call it Q. So according to this thing, Q has a n minus 1 distribution, degrees of freedom n minus 1. Right. Now notice that this quantity involves data or the observed random variables, x bar and s, both contain x1 up to xn. And in addition to that, it contains the unknown parameter mu also. So this is a function of the observed random variables and parameter. Right. But the distribution of this quantity Tn minus 1 doesn't contain any parameter. Right. So such a quantity which is a function of the data and a parameter whose distribution doesn't contain any parameter is called a pivotal quantity. So therefore, this quantity is a pivotal quantity, and it is a very useful pivotal quantity in statistical inference, especially when you want to test hypothesis concerning the mean of a normal distribution, and also when you want to construct a confidence interval for the mean of a normal distribution. Right. So this will be therefore used later on. In addition to that, I will also talk about the use of T distribution in some other situations, especially uh, when you have two independent samples from two normal distributions. So that means suppose x1 up to xn is a random sample from a normal distribution with say mean mu x and some variance sigma square. So that means x1 up to xn are IID normal with mean mu x and variance sigma square. And suppose we have another random sample y1 up to ym uh, coming from a normal distribution with mean mu y and the same variance. Let us assume that both normal distributions have the same variance, right? So y1 up to ym are therefore independent and identically distributed with the same normal distribution, right? So these x1 up to xn are independent within the sample, y1 up to ym are independent within the sample, and any xi is independent of any yj as well, right? Now let us use the known results here. Let x bar and y bar be the two sample means, and sx square and sy square be the corresponding sample variances. In this case, we are considering both sample variances with the divisor n minus 1. Now we know already that x bar in this case is normally distributed with mean mu x and variance sigma square over n. Y bar is normally distributed with mean mu y and variance sigma square over m. And because x bar and y bar are independent, x bar minus y bar will have a normal distribution with mean mu x minus mu y. Variance will be equal to the sum of these two variances, and therefore we can write it down as sigma square times 1 over n plus 1 over n, plus, not the minus. And from that, we can standardize this quantity, right, by taking away the mean and dividing by the standard deviation. Then we get this quantity, and let us call that Z. So that Z should have a standard normal distribution. That is one result that I can get from these two samples. And similarly, again, we know from the previous discussions about the chi-square distribution and so on. If you consider n minus 1 times x square divided by sigma square, that should have a chi-square n minus 1 distribution. Let's call that quantity, this quantity u. So u has a chi-square n minus 1 distribution. And similarly, m minus 1 times sy square divided by sigma square should have a chi-square m minus 1 distribution. Let's denote this quantity by v, right? And we know that the two samples are independent. This quantity contains only the data in the first sample. This quantity contains the data in the second sample only. So therefore, these two quantities, sx square and sy square, are independent. So therefore, u and v are also independent. So now we have these two independent chi-square random variables. So if you consider u plus v, that will also have a chi-square distribution, and the degrees of freedom is equal to the sum of the two degrees of freedoms. So that will give you n plus m minus 2. So u plus v has a chi-square n plus m minus 2 distribution. Now, this Z has a standard normal distribution. As a random component, it has only x bar and y minus y bar. This quantity has a chi-square distribution. As a random variable, that quantity will contain only sx square and sy square, right? So this, therefore, we will see that this Z and this u plus v are actually independent, because we know that for a normal distribution, x bar and s corresponding as sample variance are independent. right? So therefore, X bar and this quantity is independent, Y bar and this quantity is independent, and these are independent anyway because they are coming from two different samples. So therefore, X bar minus Y bar and U plus V are independent. Now notice that this quantity I have written down as n minus 1 times Sx square plus n minus 1 Sn square divided by sigma square. Uh, not sigma square is involved at this moment. So this is actually, this quantity I can write down as n minus 1 Sx square. This quantity is equal to m minus 1 Sy square divided by n plus m minus 2. Let us consider that quantity and let's call it Sp square. Right. This quantity has a name. This is called the pooled variance estimator. Notice that we assumed both populations to have the same variance. Right. So this Sx square, Sx square is actually an estimator for the sigma square coming from the first sample. Sy square is an estimator for the same variance sigma square using the second sample. Right. What I have here is a combination of those two, actually the sum of those two, weighted sum, right? Not the weighted sum, actually, the average, just the average, right? So, well, I can call it the weighted sum because this is n minus 1 times Sx square. So that is a weight here. And m minus 1 Sy square. So that is a weight. So Sx square is an estimator for sigma square from the first sample. Sy square is an estimator for the same sigma square using the second sample. So what we have here is actually the weighted average of those two estimators, right? N minus 1 is the weight here, m minus 1 is another weight. So this is the weighted average. It's called the pooled variance estimator for sigma square, right? And if you look at this quantity U plus V here, that U plus V, we can show that is equal to this n plus m minus 2 Sp square divided by sigma square. That is equal to this quantity. So therefore, now we know that this quantity has a chi-square m plus n minus 2 distribution, and therefore this quantity should have the same quantity, right? Now, yeah, this is what it is. Now, as I have showed you that x bar minus y bar and that z quantity that we looked at here, this quantity and this quantity should be now independent. Right? This the previous quantity contains x bar and y bar only as random variable. This quantity contains only sx square and sy square as random variables. Those are independent when the data are normal, right? So therefore, now if you look at z divided by the square root of u plus v divided by its degrees of freedom, it should have a t distribution with n plus m minus 2, right? So if I simplify this quantity, I get this expression here. This is the expression that I get if I simplify. That should have then a chi-square, sorry, a t distribution with n plus m minus 2 distribution. So this is again a very useful result, especially when you want to deal with the difference between the means of two normal distributions, right? So this t distribution, this quantile t has a t distribution, and this quantity is a pivotal quantity, or this quantity, we know simplify it, is a pivotal quantity again. It contains the data, x bar, y bar, and sp contains the data. And then in addition to that, it has this unknown parameter, mu x minus mu y. But the distribution of that doesn't contain any parameter. So therefore, this quantity is a pivotal quantity. Right. So this pivotal quantity, as I mentioned, is very useful when you are dealing with or when you are making inferences about the difference between the means of two independent normal distributions. Two independent normal distributions when we can assume that variances are the same. So that's a very important assumption that we should be able to make in order to use this pivotal quantity to make inference regarding mu x minus mu y. We will discuss that making inference part later on. Right. So this is a pivotal quantity useful to make inference regarding mu x minus mu y when we have two independent samples from two normal distributions with equal variance. Now, but that equal variance assumption may not be reasonable in some situations, but still we may be able to assume that our data are coming from normal distributions. So now let us consider that situation. Suppose you have a random sample, say, of size n1 from a normal distribution with mean mu1 and some variance sigma square 1, and another random sample, independent random sample, say y1 up to yn2, suppose it is coming from a normal distribution with mean mu2 and some other variance sigma 2 square. Right. So in this case, we can show that we will consider this quantity x bar minus y bar minus mu1 minus mu2 divided by the square root of the estimated standard square root of the estimated variance, or in other words, estimated standard deviation. And this quantity is also a pivotal quantity. This doesn't involve sigma squares, right? It involves only mu1 and mu2. So this can be considered as a pivotal quantity. In order to see whether it's a pivotal quantity or not, actually, we have to look at the distribution also, right? This is not an exactly a pivotal quantity, actually, but this quantity has data and parameters on both. But the distribution of this quantity is not actually an exact T distribution. It will be an approximate T distribution with some degrees of freedom. But the degrees of freedom for this approximate T distribution doesn't have a very nice form like nice equation like n plus m minus 2 like in the previous situation. Right. The degrees of freedom here for this approximate T distribution is given by this complex formula here based on the data. Actually, therefore, we are actually estimating nu for a given situation with the data. In this case, this nu is a single value. Here, I should have used simple S1 square and simple S2 square instead of capital because this is not a random variable. This is a constant. Right. So that constant is obtained using the observed sample variance from the first sample, the second sample, and with the corresponding sample sizes. So this situation, we say approximately this quantity has a T distribution with degrees of freedom approximately given by this one. And this is called the Satterthwaite approximation. Satterthwaite approximation. Right. So this is sometimes called Satterthwaite T distribution, therefore. Right. So you can see again this T distribution doesn't involve any parameter. It's coming from the data. So therefore, we can still consider this as a pivotal quantity. Right. But that is not an exact it doesn't have an exact T distribution. We assume that it has a T distribution with approximately the degrees of freedom given with this number. But according to the definition of the pivotal quantity, it can be considered as a pivotal quantity. That means this quantity can be considered as a pivotal quantity. And that will be useful again when you are constructing confidence intervals or testing hypotheses regarding the difference between the means uh, of two normal distributions, whereas we don't have to assume that the variances are equal in this case. So this situation will be more practically useful than the previous situation because, of course, really, in reality, we don't know anything about the population variances, right? So therefore, we may not be able to assume that they are equal, right? Of course, there is a way to check whether there is a possibility that they are equal, but that will be again making inference regarding the equality of the variances. Rather than that, there is no other way usually to assume that they are equal, right? So therefore, this situation where we are not assuming that the variance are equal will be more useful in statistical inference when you are testing or constructing confidence intervals regarding the two population means, right? So all those theorems were involving univariate theory, right? Univariate theory. Now we are looking at the corresponding multivariate extensions of those, right? When the data are coming from multivariate normal distributions rather than univariate normal, right? So suppose that a random vector y has a multivariate standard normal distribution with mean 0 and variance covariance matrix equal to the identity matrix. And suppose A is a real vector, n-dimensional real vector satisfying that A dash, that is A transpose times A is equal to 1. In other words, that means A1 square plus A2 square plus A3 square up to AN square is equal to 1. Right. So we are assuming that sum of the square terms in vector A is equal to 1. And in addition to that, suppose you have another matrix, real matrix, n by n symmetric idempotent matrix B, right? N by n symmetric idempotent matrix B, such that trace of B is equal to M, which is less than n here, the dimension of Y. And suppose B times A is equal to vector 0. Right? B is a matrix, A is a vector, so you get a vector here. So therefore, that is vector 0. That means when you multiply B by A, we get all the values in the vector to be 0. Right? So this is a particular assumption. And then under these conditions, if we look at this ratio, we can show that it has a T distribution with M degrees of freedom. This M is actually the trace of this B, trace of B. Right. Now let us look at a little further here. What will be A dash Y? A dash is the A transpose. So A transpose Y will be just the linear combination of it's a linear combination of the individual components of this vector Y. So it will be like A1Y1 plus A2Y2 plus A3Y3 and so on. Right. Now because uh, Y is multivariate normal, individual components are also univariate normal, and then any linear combination of those Y's will be again normal. So therefore, actually we can show that under this condition, under the condition A dash A equal to 1, we can show that A dash Y will be univariate normal with mean 0 and variance 1 in this case. That's very easy to prove. I leave it for you to prove, right? And then let's consider this y dash by. Y dash by is actually a quadratic form, right? It's a quadratic form. This thing is itself is a single random variable, right? Single random variable, and it will have a chi-square distribution under these conditions when B is a symmetric idempotent matrix with trace M, it will be equal to, it will have a chi-square distribution with M degrees of freedom, right? So what we have here is a standard normal random variable divided by the square root of a chi-square random variable divided by its degrees of freedom. And from our knowledge now, we know that therefore, and also these two quantities will be independent, right? Uh, because b times a equal to 0, right? We have shown this result when we were talking about the multivariate normal distribution. When b and a, b times a equal to 0, these two quantities are independent and therefore this should have a t distribution. Right. So this is the explanation for that one. To see this, note that a dash y has a standard normal distribution, y dash by has a chi-square distribution, and because of this condition, those two quantities are independent. Therefore, the ratio has a t distribution with m degrees of freedom. So this quantity, this result will be very useful when you are making inference about the vector of a vector of a multivariate vector, the mean vector of a multivariate normal distribution, right? So therefore, that's a useful result. Now, let us look at something called the non-central T distribution. Up to now, all the T distributions that I mentioned were central T distributions. Central T. Now, there is something called non-central T also. The central T, all the central T distributions are symmetric around 0 and they have a bell shape. And we also know that when the degrees of freedom increases, uh, the central T distribution converges to the standard normal. But for the non-central T, those properties are not there. How does a non-central T arise? We know usually a central T arises as a ratio of a standard normal uh, and a chi-square when they are independent. But the non-central T arises from a random variable, still I'm denoting it by Z, but now not a standard normal, and where Z has a normal distribution with some non-zero mean. This delta can be a positive value or a negative value, but non-zero, and variance 1, right? So suppose Z has a normal distribution with some mean delta and variance 1, and U has a chi-square new distribution, and in addition to that, suppose that Z and U are independent. In that case, if you look at this ratio, it has some distribution. That distribution is called the non-central T distribution with new degrees of freedom, and the non-centrality parameter is delta, where delta is actually the mean of this normal distribution from which the T distribution arises here. So that is the definition of the non-central T distribution. We denote it as, say, for example, this T has a non-central T distribution with new degrees of freedom and delta non-centrality parameter. This is how we denote it. T and new appears in the subscript, and then delta is appearing as within bracket. Right. Now, let us look at uh, how the shape of the central T and non-central T vary. Well, what is the difference between those two as we change the value of delta? Right. Non-central distribution, T distribution is a fixed one. That is the one that comes when the delta is equal to 0. Right. So we will have a graph. I will show you a Shiny app where I can change the value of lambda, and then we can see how the shape of the non-central T distribution varies with the value of delta. So let me now look at that. Okay, so here is the situation. I have now here a central t distribution with, I have by default, I have chosen degrees of freedom to be 5. If I want, I can change degree of freedom like this. Right. Right. So let me stick with degrees of freedom 5 here. So this is the central T, or it is the non-central T with non-central T parameter equal to 0. Now let me increase the non-central T parameter delta. So in that case, you will see another curve that shows you the non-central T distribution with 5 degrees of freedom and given delta value. So, okay. So this blue one is the central T distribution. This red one is now the non-central T with non-central T parameter zero point 0.5. Right? And if I increase this, you will see what happens. At this point, they both look like this. We know the standard normal one is anyway symmetric. The other one is also looking very symmetric at this point because the non-centered parameter is very small here. But if I increase it, now you can see that the central T is always symmetric around 0. But now the non-central T uh, is moving towards the right as I increase the central non-central parameter as a positive value. It's moving to this side, and it has a positive skewness in that case. On the other hand, if I have negative non-centrality parameters, let's change it to the negative value. Right. Okay. Now you can see if I increase negatively the non-centrality parameter, that means if I decrease the non-centrality parameter, now it's having a negatively skewed distribution. This rainbow, right? The central distribution is always symmetric around 0. It is always bell-shaped for a given fixed new value here. So now keeping this, now I will, for example, now here the non-central parameter is negative 4.5. If I increase the degree of freedom, now you can see how it changes, right? When I increase the degrees of freedom, you can see that even for the non-centrality one, it is now coming close and close to the shape of a normal distribution. Okay, so that is the behavior of the non-central T distribution. Now, finally, I mentioned here the most commonly used R functions related to a T distribution. Those are dt, pt, qt, and rt, giving respectively the probability density, cumulative probability, and the quantile and the random observations. Usually, uh, the default value for the first value is actually the dt here is a x value, or when you're calculating pt, you have to give a quantile. When you're calculating qt, you have to give a probability. When you're calculating rt, you have to give the number of observations. That is the first argument. Second argument is always the degrees of freedom. And then you can give the value of the non-centrality parameter uh, if you are dealing with a non-central t distribution. But by default, NCP is equal to 0. Therefore, if you don't give the non-central parameter, then all the things that we get are related to the central T distribution. Now, you might think, where do we need this non-central T distribution? Well, this non-central T distribution and also non-central chi-square, and also later on we'll talk about non-central F distribution. All those are very, very useful. For example, if you want to calculate something called the power of a statistical test of hypothesis. right? Especially when you are testing about the mean or the variance. We have some standard tests. When you are dealing with the statistical test, we talk about something called the power of the test. And when you are calculating the power of this test, these non-central distributions are very, very useful. So that is the end of this lesson on the T distribution, students T distribution. In the next lesson, we will talk about the F distribution.